Today let us discuss about Newton's rings. So what are these Newton's rings, how they are formed, and what are the conditions for the formation of Newton's rings, etc. We will discuss it on the basis of an experiment. Before that, let me give a clear introduction to the Newton's rings. In the previous classes, we have studied about the pattern of interference, and we have discussed about the interference in thin films. Now, these Newton's rings are best suited for non-uniform thin films. These are best suited for your non-uniform thin films. Now, when a non-uniform thin film is considered, in terms of the interference pattern occurring in the non-uniform thin film, then the Newton rings are supposed to be formed. Here, the setup is discussed as follows. Consider a plain glass plate. Consider a plain glass plate and a plano-convex lens. A plano-convex lens. Now, plano-convex lens is placed. A plano-convex lens is placed on the glass plate. On the glass plate. Okay, and in this, the convex surface meets at a point on the glass plate, which we call it as the point of contact. It is called as the point of contact. Now, in this particular case, we show it in terms of a diagram how this generally follows. Now, when that convex surface is placed exactly on the top of a glass plate, there exists a point of contact. Now, an air film is formed. An air film is formed with increasing thickness. An air film is formed with increasing thickness of the plano-convex lens. Now, let that air film has certain thickness. Okay. Now, a light from a monochromatic source is incident on the plano-convex lens. Now, when light is supposed to be incident on the plano-convex lens, it reaches at the point of contact. At the point of contact, we assume say at so it will be shown in the diagram at O, the thickness is supposed to be 0. So, the thickness is supposed to be very much small, rather 0. We can say that at the point of contact, the thickness is supposed to be 0. Next, this, if we explain it now, because of this light from a monochromatic source of light, when it falls on the surface of the plano-convex lens, then because of the interference between that is, we said an air film is supposed to be formed between the plano-convex lens and the glass plate, and because of that there exists an interference between the light which is supposed to be incident onto the surface and the reflected light coming back onto the surface. Because of those two rays, it undergoes interference, and because of that interference, Newton's rings are supposed to be formed concentric with respect to the point of contact, and those rings are called as your Newton's rings. First, what we have here is, we consider a non-uniform thin film. Generally, these Newton's rings are best suited for non-uniform thin films. Here we consider a plano glass plate, plano convex lens and a glass plate, and see that the convex surface meets with the surface of the plane glass plate. Once it meets with respect to the glass plate, at the point of contact, we assume that the thickness is supposed to be 0, and a ray of light from a monochromatic source is allowed to be incident on the plano convex lens. And once that light ray reaches the surface or the point of contact, it undergoes reflection, and the ray which is undergoing reflection will be hit back by that, and because of the air gap formed between the two lenses, that ray is supposed to be reflected onto the thin film, because of which interference pattern is supposed to be formed. And because of the interference, there exists some concentric circular rings that are formed around the point of contact, and those rings are supposed to be called as the Newton's rings. The experimental setup is as follows, or we can even call it as experimental arrangement. Now, in this experimental arrangement we have, now this is the plain glass plate. Let us consider this glass plate as say G. G is supposed to be the plain glass plate. You have a convex lens, a plano convex lens. Let us consider this is the surface of the plano convex lens. Now we are talking about this point. At this particular point of contact, the thickness is supposed to be 0. Let us call this point as O. Now here, this is what we call it as the air film. This is considered as the air film. An air film is supposed to be formed between the plain glass plate and the convex lens, which has got some increased thickness. So from here onward, the thickness keeps on increasing. This thickness, we are calling this as T, small t. Let T, small t be the thickness of the air film. Now, in this case, what we see here, we have a source of light coming out from here. This is the source of light. This source of light exactly falls onto the, it is incident normally onto this plano convex surface. Now that rays, so this is what we refer it for the, we call this as the microscope. Here we have the source, let us call this as S. This is from where the monochromatic light comes, and that monochromatic light will pass through a convex lens like this. Okay. Now this will follow, the light is supposed to be following this particular path. We are referring it to as the path. This will proceed further. Now from here, as we are viewing from here, this is exactly falling onto that normally. This is how we generally see the setup from here. Okay. From the figure, it is clearly evident that the light is supposed to be done here, and why these rays are coming is because we have an arrangement, a small arrangement where another glass plate is supposed to be placed, it is incidented in this position. The light will fall onto this one and get deviated in this pattern. So this deviation, let us see it from here. So this is the amount of deviation occurred by the light ray when it is directly falling onto the surface. So this rays will meet the contact surface. Now the angle of incidence is supposed to be around 45 degrees with respect to the viewed area. So the light rays will generally fall onto this, and they get deviated and they get reflected back onto the convex surface. So these are the light rays coming out from the source. This is your convex lens C, and from where the light will come over here and get reflected onto this surface, and the other ray comes over here and falls onto this surface. The one which is coming over here will fall and occupy the area onto the planos on the surface. So, this will get downwards as well, like this. Okay. So, this is the case. Once it meets the surface, so an air film is formed over here, it undergoes refraction over here, they get interfere with respect to the air film, and because of which a bright dark, that is let me draw this. This is the formation of the Newton's rings. So, these are the concentric circles around that particular point of contact. This is because of the interference pattern. Okay. These are what we call them as the dark bands, and the open spaces over here, what we call this as, the bright bands. Okay. Dark and bright bands which are around this darker region can be seen there. Okay. Now, this is how the pattern generally follows. This is called as these are called as the Newton's rings. So, this is the form experimental arrangement what we see here. Here we have a plain glass plate, which is given as G, and a plano convex lens. Let us call this lens as L. This is your plano convex lens L. We have a monochromatic source of light, which is given as S. So, this is your S surface. We have we call this as the collimating lens. So, a lens is provided here given by C, and this is microscope. M is supposed to be your microscope, a microscope. Then next we have another glass plate, placed at 45 degrees angle with respect to the incident rays. Okay. So, this is how the pattern is supposed to be generally followed. So, this is the convex surface what we are seeing. Okay. Let me name this point as O. Okay. So, this is how we generally form the experimental setup. From the second figure, we come to know, we can see the interference pattern that has been done with respect to the plain glass plate and the convex lens. Now, you can see from the figure, this is the plain glass plate G, this is the convex lens L. Now, this is placed at, say this is the point of contact between the glass plate and the convex lens. Now, here a light ray AB is supposed to be incident on the plano convex lens. It is meeting at the point B at the bottom of the convex lens. This amount of light ray undergoes reflection, and this amount of reflected light ray follows after getting reflected back, it is transforming to form ray 1. And when this particular amount of light ray at point B in the second sense undergoes refraction because of the air film over here, it undergoes refraction, and then that amount of refracted ray reaches the point C, and from point C it is getting reflected back and transforming to form a ray 2. Now, so here the Newton's rings are basically formed with respect to the incident ray with respect to the top of the convex lens and the bottom of the glass plate with respect to the air film of thickness small t. So, because of which the Newton's rings are supposed to be formed. Now, the path difference between these two rays, ray 1 and ray 2, with respect to the plane glass plate and the convex lens are to be found out. Therefore, we write it as the path difference. Now, before calculating the path difference, let us discuss about one more important point. The ray 1 which is getting reflected back, it is happening without any change in the path difference. That is, there is no phase difference for that one. So, phase difference is supposed to be 0 in case of ray 1, because there is no disruptions directly meeting the lower half of the convex lens that is getting reflected back without any change in the phase. So, the phase difference for ray 1 is supposed to be 0, whereas for ray 2, once it is getting refracted back and then transforming to form a ray 2, in that particular sense it is undergoing a path difference of lambda by 2. It is undergoing a path difference of lambda by 2 and a phase difference of pi. So, this is phase difference of pi. For what? This is concerned with the ray 2, whereas for ray 1 there is no change of path, the phase difference is supposed to be 0. Phase difference is 0. So, it is not undergoing any kind of a phase difference there. Now, these are the conditions for the Newton's rings to be formed. Now, if you take up the conditions for the interference pattern, as we know from our earlier classes, the path difference delta lambda is equal to 2 mu t cos r, because this is for the see here, if the ray is undergoing a phase difference of pi and the path difference of lambda by 2, so this is an additional path difference maintained by the ray 2, because of which a dark ring is supposed to be formed. So, an additional path difference of lambda by 2 is what we are considering here. So, delta lambda is equal to 2 mu t cos r plus lambda by 2. So, this is the path difference between the two rays which are undergoing reflection and refraction because of the amount of incident light as well as the air film of thickness small t. So, this is how we give the condition as equation 1. Now, here in this criteria, in this case, as we are getting through with the normal incidence, so the monochromatic light is supposed to be incident normally. For that normal incidence, the value of R is supposed to be equal to 0. For normal incidence, the value of R is supposed to be equal to 0. Now, in this case, here we find that if you substitute the value of R in the above equation, we have, as we know, cos 0 is supposed to be equal to 1. Therefore, delta lambda is equal to 2 mu t plus lambda by 2, since cos 0 degrees is equal to 1. So, 2 mu t plus lambda by 2 is delta lambda. Okay. Now, as we are dealing with the interference pattern in case of the ray 2, we are concerned with respect to the air film. So, for air, the refractive index is supposed to be equal to 1. So, we write mu is equal to 1. If we substitute the value of mu in the above equation, we have 2t plus lambda by 2 is equal to delta lambda. So, 2t plus lambda by 2 is equal to delta lambda. As we know, for the previous equations, especially for we are concerned with respect to the bright ring. So, for bright ring, in case of interference, for bright band rather, or otherwise the ring, so we write delta lambda is equal to n lambda. Okay. So, transforming that equation, we have 2t plus lambda by 2 is equal to n lambda here. Okay, n or otherwise n lambda is equal to 2t plus lambda by 2. So this is the criteria for us to frame the path difference between the two reflected light rays. Okay. Now here, in terms of our this thing, we can even transform the equations as follows, and then we can write it as 2t is equal to n lambda minus lambda by 2, which indeed will be equal to, when lambda here we write it as 2n lambda minus lambda by 2, which is equal to, take out lambda, then it will form as 2n minus 1, lambda into 2n minus 1, or you can write it as 2n minus 1 into lambda by 2. So this is how the equation gets transformed. Now we can rewrite that equation in terms of that as, so this equation which we are transforming it, and we are writing it as delta lambda is equal to 2n minus 1 into lambda by 2. This is for brighter ring. Dark ring. For dark ring, we write it as, for dark ring the same product is written as delta lambda is equal to, in terms of our this thing, that is, we are saying 2 mu t cos r plus lambda by 2, which is undergoing additional path difference, right. Now in case of that, for normal incident it is done with respect to cos r being equal to, cos 0 is equal to 1. So 2 mu t plus lambda by 2, mu is equal to 1 for air. All that equations, if at all we substitute and rewrite, the condition will get transformed as delta lambda, which is here for the bright band ring, we are stating it with respect to delta lambda in terms of this. So actually this is the condition for the bright ring. Now from this particular equation we have, let me write it over here, 2t is supposed to be equal to 2n minus 1 into lambda by 2. So this is the condition for the brighter ring. Now the same thing when we apply for the dark band, for the dark ring, we have, with reference to the same equation again, resolving it again, we can write it as 2t is equal to, the same condition gets transformed in terms of 2n plus 1 into lambda by 2. So 2t will be equal to 2n plus 1 into lambda by 2, because 2t is equal to n. In terms of our explanation, we give it in terms of the values, and we get transformed it as 2t is equal to 2n plus 1 into lambda by 2. So this is the same thing, whatever we have applied for your brighter ring, the same is applicable in case of even the dark ring as well. So 2t is equal to 2n plus 1 into lambda by 2 is the condition for the dark ring that has been formed because of the reflected rays with respect